Hello and welcome to our lesson on measuring changes in reactants and products. There are various ways you can start to calculate the rate of reaction, but you need to know either how much reactant you've lost in a certain amount of time or how much product you've gained. So the first one there, measuring the loss of reactants over time, how would you actually do that in the lab? Well, you would have something like a top pan balance, and you would have your reactants, your chemical reaction occurring actually on the top pan balance itself. And over time, you would be measuring the mass as it decreases. So you would expect the mass to decrease over time. So this doesn't work if you're making a product that's a liquid or a solid, because that's not going to escape. It's not going to do anything. This would only work if you were making a gas. So that gas escapes, and you would see the mass decreasing as the gas escapes over time. The advantage of it is it's relatively easy to do. It can be accurate. It's easy to set up. It's easy to read, and it's a good way of measuring loss of gas. Your difficulty is, your disadvantages is that you need a really precise top pan balance, because gases don't weigh much or have much mass. Unless you've got a really accurate top pan balance, you're not going to see it going down by much at all, if anything. So if you can imagine, if you've got a top pan balance that only measures per gram, it's going to take quite a long time to lose a gram of carbon dioxide or something. So you could go an entire reaction and not see much change. So you really do need a very specific, precise top pan balance that measures to at least 2 decimal places, otherwise you're just not going to get the evidence. This is the one that you do in the PAG, in the practical that you're assumed to have done. The change in appearance. Okay, so the classic example here is the sodium thiosulfate and the hydrochloric acid, and what happens is it starts off as a clear liquid, and then as more and more product is made, there is a solid product made in there, it's making sulfur, and the clear liquid goes from clear to cloudy, and eventually, if you're looking from above, that cross is going to disappear. So you draw a cross on the paper underneath, and then you measure how long it takes for that cross to disappear, because the solution has gone opaque, it's gone cloudy. So the advantage of this is, well, it's very easy to set up, it's very easy to record, anybody can do it, you don't need a lot of equipment. The disadvantage is that everybody's going to decide when that cross disappears at a slightly different time. It's not particularly an accurate way of doing things. Okay, so this is one that we often use in class, really good for measuring the volume of gas made over time. So in this example, in your conical flask, you have your reaction taking place. You're making a gas. That gas obviously rises, because gases do, and it's trapped in the delivery tube, and it takes it through, and you'll notice it goes underneath either a measuring cylinder, or in this example, a burette. And what happens is the gas pushes out the water. So it might be that the water starts up here at 0, and you can say, well, I started at 0, and after 30 seconds, it's gone down to 30, and therefore I've made 30 centimetres cubed in the first minute, or whatever. Or you might say, well, it's taken me 2 minutes to empty the tube, or whatever. So the advantage of this, well, it's easy enough to set up, it's easy enough to read, it's not particularly expensive. Burettes are expensive. We tend to use measuring cylinders because they're cheaper. Disadvantage is you've got to be really careful on where you start here. If you don't fill it up to 0, you've got to know when you need a starting point, so you know exactly how much you've made, and you'll know from experience that once you've set them up, they're okay, but setting them up to start off with is a bit of a pain. Trying to make sure that the water stays in the burette or in the measuring cylinder. Here's a point about precision and being accurate and getting precise results. So accuracy is more about what you're doing, precision is about your equipment. So your equipment here, you would use a measuring cylinder that has enough of these intervals to make the intervals smaller, so it's more precise results, accurate. You're getting down to eye level, and you're measuring the meniscus line. So that is so liquids will naturally curve in a container. You don't often see it because obviously the containers are usually wider. But in measuring something, you can see that curve. And you will always measure at the bottom of the curve. That's called the meniscus line. And if you all do that, then your results are accurate every time, because obviously there's quite a lot of difference between that point there and that point there, of course, and that's not very precise if you're using that one up there sometimes and that one there down other times. So always using the meniscus line. So you have to get down to eye level, and yeah, that makes it accurate because you're doing that, and it's precise because I'm using intervals of only 1 centimetre each time. A step up from the measuring cylinder or burette is using a gas syringe. Same idea, your reaction is going on in a conical flask, you're collecting that gas, and what happens is you obviously start here and it pushes out the plunger as it makes more and more gas. Advantage, really, really precise, easy to use. Disadvantage, gas syringes are expensive and you lot tend to break them. There's a very obvious connection here with other parts of the syllabus, and it's just testing for gases. So obviously if you're making gases, there's a logical connection in the exam. Well, how do you know it's carbon dioxide, or how do you know it's oxygen? So just kind of reminding you here that you will be linking to other parts of the syllabus. Ignore water there, you don't need to know that one. So carbon dioxide, chlorine, hydrogen and oxygen, you would need to know the test for that, and whether the gas you're making would test positive for that test or negative for that test. So how do you know what gas do you think you've made? How would you prove it? Or what would happen to this gas in lime water? Well, it's not carbon dioxide, so it would be a negative test. Nothing would happen. Okay, so that's the end of this lesson, guys. I'll see you next time.